5.2 Introduction to Rate Law. Topic overview. Since a rate of reaction can only be determined experimentally, we can use experimental data to write a rate law. A rate law describes how the rate of reaction is proportional to the concentration of each reactant raised to a power. For a generic reaction such as this one, D plus 2C yields AB. The rate law for this reaction might be found experimentally to be rate equals K times the concentration of D to the 0th power times the concentration of C to the 1st power. This reaction would be described as 0th order with respect to D and 1st order with respect to C. This means that if the concentration of D is changed, it will not affect the rate of the reaction. However, if the concentration of C is changed, then the rate of reaction will change by the same factor. If the concentration of C is doubled, then the rate is doubled. If the concentration of C is tripled, then the rate is tripled. And so on. The sum of the exponents in the rate law describes the overall rate law. The example above is a first-order reaction. There are two things to keep in mind when using rate laws. 1. The coefficients have nothing to do with the rate law, for reasons which will be explained later in the unit. 2. Rate law can only be discovered by experiment. In rate law equations, the rate constant, K, is different for each reaction and set of conditions, specifically temperature. The units for K describe the overall rate order. You will be asked to solve for this value and to provide the units of the rate constant. Remember, the rate of a reaction is measured in the change in concentration per time, so the units for K need to be whatever makes the rate equal to these units. Comparing the initial rates of each individual reactant allows us to determine how each reactant affects the rate of the reaction. We can then write a rate law for the reaction. This is often known as the method of initial rates. You should look at the tables of data provided in the problem and look for where only one variable changes to see the effect on the rate. The reaction order can be summarized by looking at the effect on the rate compared to the change in concentration. Here is an example with some real-world data, based on the equation A plus B yields 2C. In experiments 1 and 2, the initial concentrations of A were held constant, the control, and the initial concentration of B was doubled. This led to an initial rate of formation of C being doubled as well, which means that this reaction is first order with respect to B. In experiments 1 and 3, the initial concentrations of B were held constant, the control, and the initial concentration of A was tripled. This led to an initial rate of formation of C being tripled as well. We can say that this reaction is first order with respect to A. The overall rate law would be rate equals K times the concentration of A times the concentration of B. And the overall reaction order would be the sum of the exponents, which is 2. This is a second-order reaction overall. Finally, we can plug in the data from one of the experiments to solve for the value of the rate constant K, and assign units to it. We will use experiment 1 since the values are the simplest. Therefore, the rate constant, K, is equal to 0.015, and is assigned the unit per molarity per second so that, when the rate is calculated, it ends with a unit of molarity per second.